Beneath the cracked ice of a distant moon, an ocean deeper than all of Earth's seas combined lies waiting. Silent, dark, and possibly alive. This is Europa, and it may be the most important place in our solar system. Welcome to Sleepy Science Nights. Tonight, we journey to a place that has captivated scientists for decades, a frozen world orbiting Jupiter, a moon that hides something extraordinary beneath its surface. Europa is not like our moon. It does not reflect ancient craters and dead volcanic plains. Instead, Europa's surface tells a different story, one of movement, of change, of something stirring far below. For years, scientists believed that life required sunlight, that without the warmth of a star, biology could not exist. But then we discovered life in Earth's deepest oceans. Creatures thriving in absolute darkness, surviving on chemistry alone. And suddenly, the rules changed. Europa became more than just another moon. It became a possibility. The ice shell covering Europa is thicker than Mount Everest is tall. Beneath it lies an ocean with more water than all of Earth's oceans combined. And at the bottom of that ocean, heat rises from the moon's core. Energy flows through hydrothermal vents. Chemistry happens in the darkness. All the ingredients for life are there. We do not know if anything lives in Europa's ocean. We have never sent a submarine beneath its ice. We have never tasted its waters or touched its seafloor. But the evidence keeps building. The clues keep emerging. And the questions keep growing. In this video, we will explore everything we know about Europa. We will examine the ice that covers it, the ocean that hides beneath, the tidal forces that heat its core, the chemistry that might sustain life, and the missions that will soon give us answers. This is not a quick journey. We will take our time. We will explore every layer, every mystery, every possibility. So, settle in. Get comfortable. Let the gentle science wash over you. And if you enjoy this journey through the cosmos, please subscribe to Sleepy Science Nights. We explore the universe at a pace designed for rest, for wonder, for peaceful sleep. Now, let us begin our descent to Europa. Europa orbits Jupiter at a distance of 416,000 miles. This might seem far, but in cosmic terms, it is incredibly close. Our own moon sits 240,000 miles from Earth. Europa hugs its giant planet much more tightly. Jupiter dominates Europa's sky. If you stood on Europa's surface, Jupiter would appear 24 times larger than our moon appears from Earth. A massive sphere filling the horizon. Bands of orange and white clouds swirling across its face. The great red spot rotating slowly into view. But Europa does not simply orbit peacefully. It is locked in a gravitational dance with three other major moons: Io-1, Ganymede, Callisto. Together, they create a system of gravitational forces that squeeze and stretch Europa constantly. Like a rubber ball being compressed, and released, over and over, forever. This squeezing generates heat, enormous amounts of heat, enough to keep an ocean liquid beneath miles of ice, enough to power chemistry at the ocean floor, enough, perhaps, to sustain life. Europa is the sixth closest moon to Jupiter. It completes one orbit every 3.5 Earth days. But here is something remarkable. Europa always shows the same face to Jupiter, just as our moon always shows the same face to Earth. This is called tidal locking. One side of Europa perpetually faces the gas giant. The other side faces away into space. The moon itself is slightly smaller than Earth's moon. Its diameter measures roughly 1,940 miles. If you placed Europa next to Earth, it would look like a small marble beside a basketball. But size is not what makes Europa special. What makes it special lies beneath. The surface temperature of Europa averages around -260 degrees Fahrenheit, cold enough to freeze carbon dioxide solid, cold enough to turn nitrogen into liquid, cold enough that any exposed water would freeze in seconds. And yet, beneath this frozen wasteland, warmth exists. Scientists discovered Europa in 1610. Galileo Galilei pointed his telescope at Jupiter and noticed 4 bright points of light moving around the planet. He had discovered Jupiter's largest moons, Io, Europa, Ganymede, Callisto. Together, they are called the Galilean moons. For centuries, Europa remained a mysterious point of light. Telescopes improved, but Europa stayed small, distant, unknown. Then, in the 1970s, everything changed. The Voyager missions flew past Jupiter. Voyager 1 arrived in March of 1979. Voyager 2 followed in July of the same year. Both spacecraft carried cameras, and when those cameras turned toward Europa, they revealed something no one expected. Europa's surface was smooth, incredibly smooth. Where other moons showed countless impact craters, Europa showed very few. This meant the surface was young, geologically active. Something was erasing the craters. Something was renewing the surface. The images showed a world covered in ice, but not rough, chaotic ice. Instead, long cracks stretched across the surface, brown and reddish lines crisscrossing the white terrain. Scientists called them linea, linear features etched into the frozen shell. Some of these cracks ran for hundreds of miles. Some formed complex patterns. Double ridges running parallel, bands where the ice seemed to have pulled apart and refrozen, chaotic terrain where the surface looked like it had been broken into pieces and jumbled together. What could cause such features? The answer pointed to something beneath the ice, something fluid. Something that allowed the ice shell to move and crack and reform: water. After Voyager, scientists began to suspect that Europa might harbor an ocean. But suspicion is not proof. The evidence was suggestive, but not definitive. More data was needed. And in 1995, that data began to arrive. The Galileo spacecraft entered orbit around Jupiter. Unlike Voyager, which had flown past quickly, Galileo stayed. For 8 years, it circled Jupiter, making repeated flybys of the moons. It passed Europa 11 times. Each time, it gathered more information, more images, more measurements. Galileo's magnetometer detected something fascinating. As Europa orbited through Jupiter's powerful magnetic field, it created its own induced magnetic field. This only happens when an electrically conductive material exists inside a moon. And what conducts electricity better than salt water? The evidence was mounting. Europa had a liquid ocean beneath its ice. The question was no longer if the ocean existed. The question was how deep it went, how thick the ice was, and what might live in those dark waters. Galileo also revealed the ice shell's complexity. High-resolution images showed that Europa's surface was not static. Some areas looked ancient. Others looked like they had formed yesterday. The ice was moving, shifting, breaking apart, and reforming. One particularly strange feature caught scientists' attention. They called it chaos terrain, regions where the ice appeared to have completely collapsed, blocks of ice tilted at odd angles, jumbled together like a jigsaw puzzle that had been shaken apart, as if something from below had broken through, or as if the ice had melted and refrozen. Scientists developed a theory. Perhaps warm water from the ocean below occasionally reached the surface. Perhaps it melted through the ice shell in certain locations. Perhaps it brought material from the ocean depths, material that stained the ice, brown and red. Those colors fascinated researchers. Pure water ice is white, but Europa's ice showed distinct coloration, especially along the cracks and in the chaos terrain. Something was mixing with the ice. Some chemical, some mineral, something from below. Spectroscopic analysis suggested the presence of salts, magnesium sulfate, sodium chloride, the same salt that fills Earth's oceans. This made sense. If Europa's ocean was in contact with a rocky seafloor, water would dissolve minerals from the rock. Over millions of years, the ocean would become salty, just like Earth's seas. But the colors also suggested something else. Sulfur compounds, perhaps delivered by radiation from Jupiter, perhaps created by chemical reactions in the ice, perhaps brought up from the ocean itself. The chemistry was complex, fascinating, and still not fully understood. Europa's ice shell thickness remains uncertain. Estimates range from 10 miles to 15 miles thick. Perhaps thicker in some regions, perhaps thinner in others. Beneath that ice, the ocean may be 40 to 100 miles deep. That is deeper than the deepest point in Earth's oceans, deeper than the Mariana Trench. An ocean that could contain 2 to 3 times the volume of all water on Earth. Think about that for a moment. All of Earth's oceans, the Pacific, the Atlantic, the Indian, the Arctic, the Southern, all the seas, all the gulfs, all the bays, all of it combined. And Europa's ocean holds 2 to 3 times that much water, hidden beneath ice, orbiting a giant planet, 600 million miles from the Sun. At the bottom of that ocean, a rocky sea floor waits, and just as on Earth, where ocean meets rock, chemistry happens. Heat flows from the interior, minerals dissolve into water, energy becomes available, and where energy flows, life might follow. We have not yet proven life exists on Europa. We have not detected any organisms. We have not found any biological signatures. But we have found all the conditions that life requires: water, energy, chemistry, time. Europa has had billions of years for chemistry to become biology. Billions of years for simple reactions to become complex. Billions of years for something to emerge in that dark ocean. Something that does not need sunlight. Something that thrives on chemistry alone, just as life does in Earth's deepest oceans. And that is where our story truly begins. The ice covering Europa is not ordinary ice. It is not like the ice in your freezer or the ice on a winter lake. It is ancient, tortured, constantly reshaping itself under forces we are only beginning to understand. From orbit, Europa appears bright white, almost glowing. This is because the ice reflects sunlight exceptionally well. Fresh, clean water ice has one of the highest albedos of any natural surface. Europa reflects about 67% of the sunlight that hits it. For comparison, Earth's moon reflects only about 12%. This brightness tells us something important. The surface ice is relatively young. Old ice accumulates dust from space, micrometeorite impacts, radiation damage. Over millions of years, ice darkens, but Europa's ice stays bright. This means the surface refreshes itself somehow. New ice replaces old ice. The surface renews. But how? What mechanism could constantly resurface an entire moon? The answer lies in the ice shell's structure. Scientists believe Europa's ice exists in multiple layers. At the very top, a cold, brittle crust. Temperatures here reach -260 degrees Fahrenheit. Ice. This cold behaves like rock, hard, rigid, prone to cracking rather than bending. Below this frozen crust, conditions change. Pressure increases. Temperature rises slightly. The ice becomes less brittle, more plastic, capable of flowing slowly over geological time. Like a glacier on Earth, but under an alien sky, and below that, possibly a layer of warmer ice. Ice that approaches the melting point. Ice that might even contain liquid water mixed within it. A slush layer, neither fully solid nor fully liquid. Scientists call this a mushy zone. Finally, beneath all the ice, the ocean itself. Liquid water, kept from freezing by the heat generated from tidal flexing. The constant gravitational massage from Jupiter and the other moons. Heat that flows upward through the ice. heat that might occasionally break through to the surface. The surface features tell this story in frozen detail. The lineae that crisscross Europa are not simple cracks. They are complex structures. Many form double ridges, two parallel lines of raised ice with a trough between them. These ridges can rise several hundred feet above the surrounding terrain. They stretch for hundreds, sometimes thousands of miles. How do they form? Scientists have proposed several mechanisms. Perhaps cracks open in the ice shell. Water from below rushes up to fill them. The water freezes quickly in the extreme cold. Fresh ice forms, but the crack opens again. More water rises. More ice forms. Over thousands of years, ridges build up on either side of the crack. Or perhaps the process is different. Perhaps the ridges form when warmer ice from below rises like a diapier, a plume of buoyant ice pushing upward through colder, denser ice above. When it reaches the surface, it spreads sideways, creating the double ridge structure. Both mechanisms might occur. Europa's ice shell is complex enough to support multiple processes happening simultaneously in different regions. Some lineae appear dark, brown or reddish-brown. These are the youngest features. The color comes from material brought up from below. When scientists analyzed the spectral signatures of these dark streaks, they find salts, sulfates, chlorides, evidence of ocean chemistry painted across the ice. Other features look even stranger. Lenticulae or freckles dot the surface. These are small dome-like structures. They range from a few miles across to about 10 miles in diameter. Some appear smooth. Others show chaotic, broken terrain at their centers. Scientists think lenticulae form when warm ice rises from below. Imagine a blob of warm ice, slightly less dense than the ice around it. It rises slowly through the shell. When it reaches the brittle surface layer, it pushes upward, creating a dome. Sometimes the dome cracks. Sometimes it collapses. Sometimes it melts through completely, creating those chaotic terrain patches. The chaos terrain deserves special attention. These regions look like someone took a section of the ice shell, broke it into pieces, rotated the pieces randomly, and then refroze everything in place. Blocks of ice tilted at various angles. Gaps filled with smooth new ice. The whole region sitting slightly lower than the surrounding terrain. One prominent example is Connemara Chaos, a region about 37 miles across. The ice blocks here clearly came from the surrounding terrain. Scientists can match the edges like puzzle pieces. But something broke them apart. Something moved them. Something filled the gaps with new material. The leading theory suggests that warm ice or even liquid water rose from below. It melted or weakened the overlying ice shell. The ice broke into rafts. These rafts floated and rotated in the slush. Eventually, everything refroze. The blocks locked in place. New ice filled the gaps, and the whole region was left as a frozen record of this catastrophic event. How often do such events occur? We do not know. The chaos terrain regions look geologically young. Perhaps they form every few million years, perhaps more frequently, perhaps in cycles we have not yet recognized. Europa's ice shell also shows cycloidal cracks. These are curved fractures that propagate across the surface in a series of arcs. They look almost like someone traced a pattern with a compass, arc after arc after arc, connected but distinct. These features puzzled scientists until someone realized they might be caused by tidal stresses. As Europa orbits Jupiter, the gravitational forces change. The ice shell experiences maximum stress at certain points in the orbit. Cracks begin to form. But as Europa continues moving, the stress field rotates. The crack curves. When stress builds again, a new arc forms. The pattern repeats, creating those distinctive cycloidal chains. This means we can read Europa's orbital history in its surface cracks. Each arc represents a specific moment in time, a specific configuration of gravitational forces. The cracks are a diary written in ice. Radiation also affects the ice. Jupiter has an enormously powerful magnetosphere. Charged particles trapped in this magnetic field constantly bombard Europa's surface. This radiation breaks apart water molecules. It creates hydrogen and oxygen. Some hydrogen escapes to space. The oxygen remains, sometimes forming hydrogen peroxide and other oxidizing compounds. This radiation processing might actually help life. The oxidizing compounds created at the surface could eventually mix down into the ocean. They could provide chemical energy. They could serve as oxidants for metabolic reactions. Life in Europa's ocean might indirectly feed on Jupiter's radiation. But radiation also creates challenges for future missions. Spacecraft visiting Europa must be heavily shielded. Electronics must be radiation-hardened. Even with protection, the radiation limits how long a spacecraft can survive in Europa's environment. The ice shell's thickness varies across the Moon. Computer models suggest it might be thinner near the equator and thicker near the poles, thinner where tidal heating is strongest, thicker where less heat flows upward. These variations could create regions where the ocean is more accessible, places where future missions might drill through to the water below. Some scientists think the ice might be only a few miles thick in certain locations. Others believe 15 miles is more typical. The uncertainty is significant. It affects mission planning. It affects our understanding of heat flow. It affects our estimates of how often the ocean and surface interact. One thing seems certain: the ice shell is not a static barrier. It is dynamic, active, constantly changing. It breaks, it flows, it subducts, it resurfaces. The ice shell is not sealing the ocean away from the universe. It is a membrane, a boundary where ocean meets space, where chemistry meets radiation, where life, if it exists, might occasionally leave traces we could detect. And those traces are what we hope to find. Beneath the ice, darkness reigns, complete and absolute. No sunlight penetrates miles of frozen water. No stars shine through. The ocean of Europa exists in perpetual night, yet this ocean is not lifeless and still. It moves. Currents flow through its depths. Heat rises from below. Cold descends from above. The water circulates in patterns we can only imagine. On Earth, ocean currents are driven primarily by wind and by temperature differences created by sunlight. But Europa has no wind, no atmosphere to speak of, and no sunlight reaches the ocean. So what drives the currents? The answer is heat. Tidal heating warms Europa's rocky interior. That heat flows upward through the ocean. Warm water rises. Cold water sinks. Convection cells form. Large-scale circulation patterns develop. The ocean mixes itself through temperature differences alone. Scientists estimate the ocean contains about 3 billion cubic miles of water. To put that in perspective, Earth's oceans contain about 321 million cubic miles. Europa's ocean holds roughly 10 times as much water as all of Earth's seas combined. That is an almost incomprehensible amount of water, a global ocean wrapping around the entire moon, uninterrupted by continents or islands. A single body of water stretching from pole to pole, from the ice ceiling above to the rocky floor below. The ocean's depth likely varies. Computer models suggest it might be 60 miles deep in some regions, perhaps 100 miles in others. These are estimates based on gravity measurements and magnetic field data. We have never actually measured the ocean directly. The water is almost certainly salty. When liquid water contacts rock, it dissolves minerals. Over billions of years, salts accumulate. Sodium chloride, magnesium sulfate, potassium chloride, the same salts that make Earth's oceans taste of the sea. This salinity matters for several reasons. First, it lowers the freezing point of water. Pure water freezes at 32 degrees Fahrenheit. But salty water can remain liquid at much colder temperatures. This helps keep Europa's ocean from freezing despite the moon's distance from the sun. Second, salinity affects density. Salty water is denser than fresh water. This creates additional dynamics in the ocean. Salt gradients can drive circulation. They can create layers within the ocean. They can affect how heat moves through the water. Third, dissolved salts provide chemistry. They make the water conductive. They enable reactions. They supply elements that life might need. Sodium, chlorine, sulfur, magnesium, all dissolved in Europa's dark sea. The temperature of the ocean remains uncertain. At the top, just beneath the ice, the water hovers near freezing, perhaps 28 degrees Fahrenheit, cold enough that any movement toward the surface results in immediate freezing. But deeper down, temperatures rise. Models suggest the bulk of the ocean might average around 40 degrees Fahrenheit, not warm by human standards, but well above freezing, comfortable for many forms of life on Earth. At the very bottom, near hydrothermal vents if they exist, temperatures could spike much higher. On Earth, Hydrothermal vent fluids can reach 700 degrees Fahrenheit, though by the time those fluids mix with surrounding seawater, temperatures drop to more moderate levels. The pressure at the ocean floor is immense. On Earth, the deepest part of the ocean is the Mariana Trench. It reaches down nearly 7 miles. The pressure there exceeds 16,000 pounds per square inch, enough to crush most submarines. Europa's ocean might be 10 times deeper than the Mariana Trench. The pressure at the bottom could exceed 160,000 pounds per square inch. This creates an environment utterly alien to surface life. But many organisms on Earth thrive under extreme pressure. Life adapts. The ocean likely exists in distinct layers. At the top, a cold boundary layer, water in direct contact with the ice ceiling. This layer probably experiences the most mixing with surface materials. Ice melts into it. Surface chemistry mixes down into it. Radiation products from the surface eventually reach it. Below that, the main ocean body, relatively uniform temperature, well mixed by convection. This would be the largest volume of water. The open ocean of Europa. At the bottom, another boundary layer. Water in contact with the rocky seafloor. This is where the most interesting chemistry might occur, where heat emerges from below, where minerals dissolve, where energy becomes available for life. The seafloor itself is probably similar to Earth's oceanic crust, basalt rock, rich in iron and magnesium, perhaps dotted with hydrothermal vents, perhaps covered in sediment that has settled over billions of years. On Earth, hydrothermal vents create oases of life in the deep ocean. Hot, mineral-rich water erupts from the seafloor. Bacteria colonize the vents. They harvest chemical energy. They form the base of a food chain that includes tubeworms, clams, shrimp, and fish, all living in complete darkness, all surviving without photosynthesis. Could similar ecosystems exist on Europa? The chemistry would differ. The organisms would be alien. But the principle might be the same. Energy flowing from the interior. Chemistry happening at the boundary. Life emerging to exploit that energy. We do not know if Europa's seafloor hosts active volcanism. We do not know if hydrothermal vents exist there. But the tidal heating that keeps the ocean liquid must manifest somewhere. Heat must escape from the interior, and hydrothermal vents are one of the most efficient ways for that heat to emerge. The ocean might also contain organic molecules, carbon compounds, the building blocks of life. These could come from several sources. Comets might have delivered organics when they impacted Europa billions of years ago. Chemical reactions in the ocean might create simple organic molecules. Radiation processing of carbon dioxide ice on the surface might produce complex organics that eventually mix into the ocean. Whatever organic chemistry exists in Europa's ocean, it has had billions of years to evolve. Billions of years for simple molecules to become complex. Billions of years for chemistry to explore possibilities. Billions of years for life, perhaps, to emerge. And that possibility is what drives our fascination. That possibility is what compels us to send missions. That possibility is what makes Europa one of the most important destinations in the solar system. Beneath the ice, in the darkness, an ocean waits, silent, patient, keeping its secrets. For now, Europa does not orbit Jupiter alone. 3 other large moons share the system. Io, the innermost, Ganymede, the largest, Callisto, the outermost. Together, they create a gravitational symphony, a dance of worlds that has profound consequences for Europa. The moons are locked in what scientists call orbital resonance. For every orbit Ganymede completes, Europa completes exactly 2. And for every orbit Europa completes, Io completes exactly 2. This is not coincidence. It is a stable gravitational arrangement that has persisted for billions of years. This resonance means the moons regularly align. Io, Europa, and Ganymede line up on the same side of Jupiter at predictable intervals. When they align, their combined gravitational pull affects each moon's orbit. The orbits become slightly elliptical rather than perfectly circular. An elliptical orbit means the distance between Europa and Jupiter changes. At closest approach, called periapsis, Europa sits about 414,000 miles from Jupiter. At farthest distance, called apoapsis, it reaches 418,000 miles away. A difference of about 4,000 miles. This might not seem significant, but Jupiter's gravity is immense. The gas giant contains more mass than all other planets in the solar system combined. Its gravitational field is correspondingly powerful. And even small changes in distance create enormous differences in gravitational force. As Europa orbits, Jupiter's gravity squeezes it. At periapsis, when Europa is closest, the gravitational pull is strongest. Jupiter pulls the near side of Europa more strongly than the far side. This creates a tidal bulge. Europa stretches slightly toward Jupiter. At apoapsis, when Europa is farthest away, the tidal force is weaker. Europa relaxes slightly. The bulge diminishes. But Europa is also tidally locked. It always shows the same face to Jupiter. This means, as the moon orbits and the tidal force changes, the bulge does not migrate around the moon. Instead, the entire moon flexes. The shape changes. The interior deforms. This constant squeezing and relaxing generates heat through friction. Just as bending a paperclip back and forth makes it warm, flexing Europa's interior creates thermal energy. Scientists call this tidal heating, and it is enormously powerful. Calculations suggest tidal heating generates enough energy to melt the interior, enough to maintain a global ocean, enough to potentially drive hydrothermal activity on the seafloor. The exact amount of heat generated depends on how rigid or flexible Europa's interior is, but estimates range from billions to trillions of watts of power. To put this in perspective, Earth's internal heat flow is about 47 trillion watts. This comes mostly from radioactive decay of elements in Earth's mantle and crust. Europa's tidal heating might generate a significant fraction of that amount, despite being much smaller than Earth. The heat distribution across Europa is not uniform. Tidal stresses are strongest at the equator and weakest at the poles. This means more heat is generated in equatorial regions. The ice shell might be thinner there. The ocean might be warmer. Surface features might be more active. Scientists can model these tidal forces using complex computer simulations. They input Europa's orbital parameters, Jupiter's mass, the gravitational influences of the other moons, the properties of ice and rock. The models calculate how much Europa deforms and how much heat is generated. These models help predict where the ice might be thinnest, where the ocean might be closest to the surface, where future missions might best target their investigations. But the models have uncertainties. We do not know exactly how rigid Europa's ice shell is. We do not know precisely how thick the ocean is. We do not know the exact composition of the rocky interior. All these factors affect how much tidal heating occurs and where that heat goes. One particularly interesting effect of tidal forces is the creation of stress patterns on the surface. As Europa flexes, the ice shell experiences tension and compression. Cracks form where the stress exceeds the ice's strength. These cracks follow predictable patterns based on the orbital mechanics. Scientists have mapped these stress patterns. They align remarkably well with the observed lineae on Europa's surface. This confirms that tidal forces are actively shaping the Moon. The cracks we see are not ancient features. They are ongoing consequences of Europa's orbital dance. The same tidal forces also affect the ocean. As Europa flexes, the ocean sloshes slightly. Tidal currents flow through the water. These currents might be weak compared to wind-driven currents on Earth, but over time they contribute to mixing the ocean. They help distribute heat. They prevent stratification. Io, Europa's inner neighbor, experiences even stronger tidal forces. Io is closer to Jupiter. Its orbit is more elliptical. The tidal heating is so intense that Io is the most volcanically active body in the solar system. Its surface is covered with active volcanoes. Sulfur erupts continuously. The entire Moon is being turned inside out by tidal forces. Europa experiences less extreme heating than Io, but the principle is the same. Orbital mechanics converts to internal heat. Gravity becomes the engine that powers geological activity. Ganymede, Europa's outer neighbor, also experiences tidal heating. But Ganymede is larger and farther from Jupiter. The tidal forces are weaker. Ganymede has an ocean too, but its ice shell is much thicker, perhaps 90 miles thick. The ocean is less accessible, less connected to the surface. Europa sits in a sweet spot, close enough to Jupiter for significant tidal heating, far enough that the radiation is somewhat less intense than at Io, large enough to retain an ocean, small enough that the ice shell is relatively thin. This combination of factors makes Europa perhaps the most promising place to search for life beyond Earth. Not because we know life exists there, but because all the necessary conditions are present: water, energy, chemistry, time. The tidal forces that heat Europa have operated for billions of years. They will continue for billions more. This is not a temporary phenomenon. It is a fundamental characteristic of Europa's existence. As long as the orbital resonance persists, the heating continues. The ocean remains liquid. The possibility of life remains open, and that possibility draws us forward, compels us to explore, demands that we visit this distant moon and see what secrets it holds. Life requires chemistry. Not just any chemistry, but specific types of reactions that can store and transfer energy. On Earth, most life uses oxygen. We breathe it. We burn food with it. We extract energy through oxidation. But oxygen comes from photosynthesis, from sunlight. Europa's ocean has no sunlight. No photosynthesis, no obvious source of oxygen, yet life might still be possible through alternative chemistries. Chemistries that do not depend on the sun. Chemistries that operate in complete darkness. On Earth, we have examples of such life. They exist in the deep ocean, in caves, kilometers underground, in toxic hot springs. These organisms do not use photosynthesis. They use chemosynthesis. They harvest energy from chemical reactions alone. The most famous examples live near hydrothermal vents. Hot, mineral-rich water erupts from the seafloor. This water contains dissolved chemicals: hydrogen sulfide, methane, hydrogen gas, iron compounds, manganese. These chemicals react with seawater. The reactions release energy. Bacteria at the vents capture this energy. They use it to build organic molecules from carbon dioxide. They become the base of a food chain. Larger organisms eat the bacteria. Still larger organisms eat those. An entire ecosystem powered by chemistry. Could similar chemistry occur on Europa? The answer depends on what elements and compounds exist in the ocean and on the seafloor. We know Europa has water. We know it has rock. We know tidal heating generates warmth. These basics are established. But the details matter enormously. What kinds of rock make up the seafloor? What minerals are present? What gases are dissolved in the ocean? Scientists have developed models based on what we know about moon formation and geological processes. Europa's rocky interior likely resembles Earth's oceanic crust, basalt, rich in iron, magnesium, and silicon. When hot water contacts this rock, minerals dissolve. Chemical reactions occur. One particularly important reaction involves serpentinization. This happens when water reacts with olivine, a common mineral in basalt. The reaction produces several products: magnetite, serpentine minerals, and hydrogen gas. Hydrogen gas is chemically powerful. It can react with many other compounds. It can serve as food for certain types of bacteria. On Earth, organisms called methanogens consume hydrogen and carbon dioxide to produce methane. Other organisms oxidize hydrogen with sulfate to gain energy. If serpentinization occurs on Europa's seafloor, hydrogen gas would bubble up into the ocean. It would become available for biological use. Any organisms that evolved to consume hydrogen would have a steady energy source. They would not need sunlight. They would not need oxygen. Just hydrogen and the right chemical partners. Sulfur might also play a role. Europa's surface shows sulfur compounds. Some probably came from volcanic material ejected by Io and scattered across the Jupiter system. Some might have come from comets. Some might have been produced by radiation chemistry. If sulfur reaches Europa's ocean, it could dissolve as sulfate. Sulfate can serve as an electron acceptor. Certain bacteria use sulfate the way we use oxygen. They oxidize organic matter or hydrogen with sulfate instead of oxygen. The process is less efficient than using oxygen, but it works. It sustains life in Earth's deep ocean sediments. Methane is another possibility. If life exists in Europa's ocean, it might produce methane as a waste product, or methane might form through geological processes. Either way, methane could become food for other organisms. Methanotrophs on Earth consume methane and thrive in various environments. Iron chemistry might contribute as well. Iron exists in multiple oxidation states. Ferrous iron, ferric iron. Organisms can shuttle electrons between these states and extract energy. Iron-based metabolism is ancient on Earth. It might have been among the first energy sources life ever used. The ocean likely contains carbon dioxide. This could come from the rocky interior. Carbon dioxide dissolves readily in water, especially under high pressure. It could serve as a carbon source for building organic molecules. All life needs carbon. Europa's ocean could provide it. Nitrogen is essential for life as we know it. Proteins require nitrogen. DNA requires nitrogen. Without nitrogen, Earth-style biochemistry cannot function. We do not know if Europa has nitrogen. Ammonia might exist in the ice or ocean. Nitrogen gas might be trapped in the interior, or nitrogen might be scarce. This uncertainty represents a significant gap in our knowledge. Future missions need to determine nitrogen availability. It could be a limiting factor for life. Or Europa's organisms might use alternative biochemistry that does not require nitrogen. Life is adaptable. Phosphorus is another critical element. On Earth, phosphorus forms the backbone of DNA and RNA. It plays a role in energy storage molecules like ATP. Most organisms cannot survive without phosphorus. Europa's rocks likely contain some phosphorus. Whether enough leaches into the ocean remains unknown. Trace elements matter too. Molybdenum, cobalt, nickel, zinc. These metals serve as cofactors in enzymes. They enable specific biochemical reactions. Earth life depends on dozens of trace elements. Europa would need to provide similar chemical diversity to support complex life. The pH of Europa's ocean is another variable. Is the water acidic, neutral, alkaline? pH affects which minerals dissolve. It affects which reactions occur. It affects which organisms could survive. Earth's ocean is slightly alkaline with a pH around 8. Europa's ocean might be similar, or it might be quite different. Temperature gradients create additional opportunities. Cold water near the ice ceiling. Warm water near the seafloor. Some organisms prefer cold, others prefer heat. A range of temperatures means a range of possible niches. More diversity, more opportunities for life. Chemical gradients matter as much as temperature. Where two different water masses meet, chemistry happens. Reduced compounds from hydrothermal vents mix with oxidized compounds from the surface. The boundary between them becomes a reaction zone. On Earth, organisms colonize these boundaries. They exploit the mixing. They harvest the energy. Europa's ocean might have many such boundaries. Vertical gradients. Horizontal gradients. Places where chemistry is most dynamic. These would be the first places to search for life. The places where energy flows most readily. We cannot yet sample Europa's ocean chemistry directly. We cannot measure its pH or test for dissolved gases. But we can make educated guesses based on physics and geology. And those guesses suggest that Europa has the chemical diversity needed for life. Not life as we know it, perhaps, but life nonetheless. To understand what life might look like on Europa, we must first look at life in Earth's most extreme environments. Places where sunlight never reaches, where pressure crushes, where temperatures swing from freezing to boiling. Places that, until recently, we thought were lifeless. The deep ocean floor was once considered a desert. Scientists in the early 20th century believed nothing could survive in such conditions. No light meant no photosynthesis. No photosynthesis meant no food. No food meant no life. The logic seemed sound. Then, in 1977, everything changed. A research submarine named Alvin explored the Galapagos Rift, a volcanic ridge on the Pacific Ocean floor. The depth exceeded 8,000 feet. The pressure exceeded 3,600 pounds per square inch. Darkness was absolute. The scientists aboard Alvin expected barren rock. Instead, they found gardens, dense clusters of life surrounding hydrothermal vents, giant tube worms up to 8 feet long, clams the size of dinner plates, white crabs, pink fish, shrimp by the thousands, all thriving in conditions that should have been uninhabitable. The tube worms fascinated researchers most. These creatures had no mouth, no digestive system, no obvious way to eat. Yet they grew large and healthy. How? The answer lay in their tissues. Inside each tube worm lived billions of bacteria, symbiotic bacteria that converted hydrogen sulfide into organic compounds. The bacteria fed the tube worm. The tube worm provided the bacteria shelter and access to chemicals. This was chemosynthesis, life powered by chemistry rather than sunlight. The bacteria used hydrogen sulfide from the vents as an energy source. They combined it with oxygen from seawater. The reaction released energy. That energy drove the creation of organic molecules from carbon dioxide. The tube worms were not alone. The entire ecosystem depended on chemosynthetic bacteria. Some lived free in the water. Others colonized surfaces. Still others lived inside larger organisms. All harvested chemical energy from the vent fluids. Since that first discovery, scientists have found hydrothermal vent communities throughout the world's oceans: Mid-Atlantic Ridge, Juan de Fuca Ridge, East Pacific Rise, Marianas Trench. Everywhere volcanic activity releases hot water into the deep ocean, life appears. But vents are not the only deep ocean ecosystems. Cold seeps also support dense life. These are places where methane or hydrogen sulfide seeps slowly from the seafloor. No hot water, no dramatic eruptions, just a steady trickle of chemicals. And yet, life congregates there too. Methane seeps host bacteria that consume methane. These bacteria often live in partnership with clams or mussels. The mollusks provide a safe place for bacteria. The bacteria provide food. Together, they thrive on methane that seeps from deep sediments. Even more extreme are the organisms living in ocean floor sediments. Miles below the seafloor, in rock pores and cracks, microbes survive on minimal energy. They metabolize so slowly that a single generation might take centuries. They exist in a state barely distinguishable from dormancy. Yet they are alive, reproducing, evolving. These deep biosphere organisms show us the minimum requirements for life. Very little energy, very little space, very little time to do anything. Yet they persist. They survive. They prove that life can exist on almost nothing. What do all these organisms have in common? They do not need sunlight. They do not need oxygen produced by photosynthesis. They need only three things: liquid water, chemical energy, and time. Europa has all three. The organisms at Earth's hydrothermal vents live in conditions remarkably similar to what we expect on Europa: darkness, high pressure, chemical-rich water, temperature gradients. The main difference is temperature. Earth's vent fluids can exceed 600 degrees Fahrenheit. Europa's vents, if they exist, would be cooler, but many vent organisms prefer the cooler water surrounding the vents rather than the hot water itself. Some Earth organisms thrive in permanent cold. Psychrophiles, cold-loving microbes. They live in Antarctic ice. In Arctic permafrost, In the cold, deep ocean, they have evolved anti-freeze proteins, special enzymes that function at low temperatures, flexible cell membranes that do not freeze solid. If life exists on Europa, it is almost certainly psychrophilic. The ocean temperature probably averages around 40 degrees Fahrenheit. That is cold by most standards, but many Earth organisms consider that comfortable. Pressure is another factor. Europa's ocean might be 60 to 100 miles deep. The pressure at the bottom would be immense, far greater than the deepest parts of Earth's oceans. Yet, we know life can adapt to pressure. Organisms in the Mariana Trench survive pressures exceeding 16,000 pounds per square inch. They have specialized proteins, compacted cell structures, chemical adaptations that prevent pressure from disrupting their biology. Europa's organisms would need similar adaptations. But pressure alone does not prevent life. It merely requires adjustment. Radiation presents a unique challenge. Jupiter's magnetosphere bathes Europa in high-energy particles. The surface receives intense radiation. Anything living there would be quickly destroyed. But the ocean is shielded. Miles of ice absorb the radiation. The water itself provides additional protection. Organisms in the ocean would experience radiation levels comparable to Earth's deep ocean, manageable, not harmful. In fact, radiation might help. As radiation breaks apart water molecules at the surface, it creates oxidizing compounds, hydrogen peroxide, oxygen. These compounds could eventually mix down into the ocean. They could serve as electron acceptors. They could enable more efficient metabolism than purely reduced chemistry allows. On Earth, the transition from anaerobic to aerobic metabolism was transformative. Oxygen-breathing organisms extract far more energy from food than anaerobic organisms can. If Europa's ocean receives oxidizing compounds from the surface, life there might evolve oxygen-based metabolism, not through photosynthesis, but through radiolysis. Radiation chemistry creating the oxidants that life requires. This possibility excites astrobiologists. It suggests Europa could support not just simple microbes, but complex ecosystems. Not just bacteria, but perhaps larger organisms. Not just survival, but thriving. Of course, this remains speculation. We have not detected life on Europa. We have not sampled its ocean. We have not found any biological signatures, but Earth's deep ocean life proves the concept. Life in permanent darkness is possible. Life without photosynthesis is possible. Life in extreme conditions is not just possible, but common. If life emerged once in Europa's ocean, it has had billions of years to adapt, to diversify, to explore every possible niche. The question is not whether life could exist there. The question is whether it does. And that is what we must discover. How do you search for life on a world covered in ice? How do you detect organisms swimming in an ocean you cannot see? How do you prove something lives in water buried beneath 10 miles of frozen shell? These questions have driven decades of mission planning and scientific debate. The most direct approach would be to drill through the ice, to lower a probe into the ocean, to sample the water directly, to look for cells under a microscope, to sequence DNA if it exists, to culture organisms in a laboratory. This would provide definitive answers. But drilling through 10 miles of ice on another world is extraordinarily difficult. It requires enormous energy, specialized equipment, years of operation. The technology exists, but barely. And the challenges multiply when you must operate robotically, with no humans present, with commands delayed by light travel time, with no ability to make repairs. So scientists have developed alternative strategies, ways to search for life without drilling to the ocean, ways to detect biological signatures from orbit or from the surface, ways to find evidence even if we cannot directly sample living organisms. One approach focuses on the surface ice. If material from the ocean occasionally reaches the surface, it might carry biological signatures. Organic molecules, chemical patterns, isotope ratios, things that hint at life below. The chaos terrain regions are particularly interesting. These areas look like the ice melted and refroze. Perhaps ocean water reached the surface. Perhaps it brought dissolved materials with it. Perhaps those materials remain trapped in the refrozen ice. A lander could visit a chaos terrain region. It could collect ice samples, analyze them with sophisticated instruments, look for amino acids, search for lipid molecules, test for specific chemical signatures associated with biology. Amino acids are particularly useful. Life on Earth uses 20 standard amino acids to build proteins, but amino acids come in two mirror image forms, left-handed and right-handed. Non-biological processes create equal amounts of both, but life on Earth uses exclusively left-handed amino acids. If Europa's ice contains amino acids that are predominantly one-handedness, that would suggest biology. Lipids are another target. Cell membranes on Earth consist of lipid molecules. These have distinctive structures. Long carbon chains attached to phosphate groups. If similar molecules appear in Europa's ice, especially in high concentrations, life becomes a strong possibility. Isotope ratios offer additional clues. Life preferentially uses lighter isotopes, carbon-12 over carbon-13, nitrogen 14 over nitrogen-15. This creates detectable patterns. If organic molecules in Europa's ice show these preferences, biology is a plausible explanation. But surface sampling has limitations. Radiation constantly bombards the surface. It breaks down organic molecules. It erases biological signatures. Material that sits on the surface for thousands of years might retain no trace of its biological origin. Only freshly exposed material would preserve clear signatures. Another approach examines plumes. The Hubble Space Telescope has detected what might be plumes of water vapor erupting from Europa's surface. Geysers shooting hundreds of miles into space. If these plumes exist, they offer an incredible opportunity. A spacecraft could fly through a plume. It could sample the material without landing, without drilling. The plume would bring ocean material directly to space. The spacecraft's instruments could analyze it immediately. Look for organic molecules. Test for biological signatures. Search for cells. This is not science fiction. NASA's Cassini spacecraft flew through plumes erupting from Enceladus, one of Saturn's moons. The instruments detected water vapor, salt, silica particles, and complex organic molecules. The plumes provided a window into Enceladus's subsurface ocean without any need to land or drill. Europa's plumes, if they are real, would offer similar opportunities, but they appear to be intermittent. They do not erupt continuously. Timing would be critical. A spacecraft would need to arrive when a plume is active. Otherwise, the opportunity is lost. Remote sensing from orbit provides another avenue. Instruments can analyze light reflected from Europa's surface. Different molecules absorb and reflect light at specific wavelengths. By measuring these wavelengths precisely, scientists can identify what compounds are present. Spectroscopy has already revealed salts on Europa. Sulfates, chlorides, water ice. Future missions with more sensitive instruments might detect organic molecules, if concentrations are high enough. If the molecules have not been destroyed by radiation. Another strategy looks for disequilibrium chemistry. Life creates chemical imbalances. It takes molecules that should not coexist and puts them together. Oxygen and methane, for example. In equilibrium, these react with each other. But on Earth, life produces both. Photosynthesis creates oxygen. Bacteria create methane. Both exist in the atmosphere simultaneously because life constantly replenishes them. If Europa's ocean contains chemical combinations that should not persist, life might explain them, hydrogen and oxidized compounds together. Reduced carbon and oxidized sulfur. Patterns that make no sense geologically, but perfect sense biologically. Detecting such patterns requires understanding Europa's geology thoroughly. We need to know what chemistry should occur naturally. Only then can we recognize chemistry that requires biology to explain. Morphology offers another potential signature. On Earth, some bacteria create distinctive structures: stromatolites, microbial mats, filaments, patterns that are difficult to explain through purely geological processes. If similar structures exist in Europa's ice or on its ocean floor, they might indicate life. But morphology is tricky. Many geological processes create patterns that look biological. Mineral crystals can form branching structures. Chemical gradients can create layered deposits. Without additional evidence, morphology alone proves little. The most ambitious approach involves a submersible, a robotic submarine designed to explore Europa's ocean. It would need to carry cameras, chemical sensors, sampling equipment. It would need to navigate autonomously, make decisions without human input, survive in extreme conditions for months or years. This concept pushes the boundaries of current technology, but it is not impossible. Engineers have designed prototype submersibles for Europa. They have tested them in Earth's oceans, under ice in Antarctica, in deep water, proving that the basic concept works. A Europa submersible would search for hydrothermal vents, look for concentrations of life, sample water at different depths, image the seafloor, document whatever exists in that alien ocean. This represents the ultimate goal: direct exploration, seeing with our own cameras, touching with our own instruments, knowing with certainty what lives or does not live in Europa's ocean. But such a mission lies years in the future. First, we must take smaller steps. Orbital reconnaissance, surface sampling, plume analysis. Each mission builds knowledge. Each answer raises new questions. Each discovery guides the next step. The search has only begun. In October 2024, a spacecraft left Earth. Carried by a SpaceX Falcon Heavy rocket, it began a journey of 1.8 billion miles. The destination, Europa. The mission, Europa Clipper. And the goal, to determine whether Europa could support life. Europa Clipper is not designed to find life directly. It will not drill through the ice. It will not sample the ocean. It will not search for cells or DNA. Instead, it will answer fundamental questions about Europa's habitability. Does the ocean exist? How thick is the ice? What chemistry occurs on the surface? Where are the best places to search for life in the future? The spacecraft is enormous by modern standards. With solar panels extended, it spans over 100 feet. The largest spacecraft NASA has ever built for a planetary mission. It needs to be large to carry all the necessary instruments and to generate enough power from sunlight at Jupiter's distance. Europa Clipper will not orbit Europa directly. Instead, it will orbit Jupiter and make repeated flybys of Europa. 49 flybys over the course of the mission. Each flyby lasting only a few hours, but each flyby gathering enormous amounts of data. Why not orbit Europa? The radiation. Jupiter's magnetosphere creates an intense radiation environment around Europa. A spacecraft in orbit would be bombarded constantly. Electronics would degrade. Instruments would fail. The mission would be short. By orbiting Jupiter instead, Europa Clipper spends most of its time outside the worst radiation. It dips in for each flyby, gathers data quickly, then retreats to a safer distance. This extends the mission lifetime from months to years. The spacecraft carries 9 science instruments, each designed to answer specific questions about Europa. The cameras will map the surface in incredible detail. High-resolution images showing features as small as 20 inches across. Color images revealing the chemistry of different regions. Stereo images creating three-dimensional maps of the terrain. The ice-penetrating radar will probe beneath the surface. Radio waves will pass through the ice. Some will reflect back from the ocean below. By measuring the time delay, scientists can calculate ice thickness, They can identify places where the ice is thin, places where future missions might drill. The magnetometer will measure Europa's magnetic field. As Europa moves through Jupiter's magnetic field, the ocean generates its own induced field. By measuring this carefully, scientists can determine the ocean's depth, its salinity, its electrical conductivity, all without ever seeing the water directly. The gravity science investigation uses the spacecraft's radio signals. As Europa Clipper flies past, Europa's gravity pulls on it slightly. This changes the spacecraft's velocity. By measuring these velocity changes precisely, scientists can map Europa's internal structure, determine how mass is distributed, confirm the ocean's existence and characteristics. The thermal instrument will map surface temperatures. Most of Europa is uniformly cold, but if warm spots exist, they might indicate places where the ocean is closer to the surface, places where heat escapes more readily, places where ice might be thinner. The ultraviolet spectrograph will watch for plumes. Water vapor erupting from the surface absorbs ultraviolet light. By watching Europa's limb as it passes in front of Jupiter or stars, the instrument can detect plumes, determine their frequency, their locations, their composition. The mass spectrometer will sample Europa's thin atmosphere. And if the spacecraft flies through a plume, it will analyze that directly, measure the molecules present, search for organic compounds, look for salts and other ocean materials. The surface dust analyzer will capture tiny particles, ice grains ejected from Europa by micrometeorite impacts, material from plumes if they exist. Each particle carries information about Europa's composition, about the ice, about the ocean below. The plasma instrument will measure charged particles around Europa, how the moon interacts with Jupiter's magnetosphere, how material escapes from the surface, how radiation affects the ice. Together, these instruments will revolutionize our understanding of Europa. They will answer questions we have been asking for decades. And they will undoubtedly raise new questions we have not yet thought to ask. The mission timeline is carefully planned. Europa Clipper will arrive at Jupiter in April 2030. It will spend several months adjusting its orbit. Then the flybys begin. Each flyby targets a specific region of Europa. Each has specific scientific goals. Some flybys will focus on mapping the surface. Others will measure ice thickness. Some will search for plumes. Others will analyze surface composition. The flybys are designed to complement each other, to build a comprehensive understanding piece by piece. The spacecraft flies at different altitudes during different passes, some as low as 16 miles above the surface, others at several hundred miles. Lower flybys provide better resolution but higher radiation exposure. Higher flybys are safer but see less detail. The mission balances these factors carefully. Europa Clipper will also observe Europa's interaction with Jupiter's magnetosphere. This interaction creates auroras on Europa, glowing regions where charged particles hit the atmosphere. These auroras reveal information about the ocean below, about magnetic fields, about conductivity. The spacecraft will operate for at least 4 years in the Jupiter system, possibly longer if systems remain healthy. It carries enough fuel for the planned mission, enough redundancy to handle failures, enough shielding to survive the radiation environment. But eventually, the radiation will take its toll. Electronics will degrade, solar panels will lose efficiency, systems will begin to fail. When that happens, the mission will end. Europa Clipper will be intentionally crashed into Ganymede or ejected from the Jupiter system. This prevents it from contaminating Europa with Earth microbes. Planetary protection is a serious concern. We must not accidentally introduce Earth life to Europa. The spacecraft was assembled in clean rooms, sterilized with heat and chemicals, documented meticulously. The probability of contaminating Europa is kept extremely low. Europa Clipper represents decades of planning and preparation. Hundreds of scientists and engineers contributed to its design. Thousands of people worked to build it. It carries the hopes of everyone who wonders whether life exists beyond Earth. The spacecraft will not answer that ultimate question. It will not say definitively whether life exists on Europa, but it will tell us where to look, what to look for, whether the search is worth continuing. And if Europa proves truly habitable, if the conditions seem right for life, then the next mission will go further. We'll drill through the ice. We'll sample the ocean. We'll search for life directly. Europa Clipper is the first step, the reconnaissance mission, the pathfinder. But it is a crucial step. And it is happening now. Europa Clipper is only the beginning. If its findings confirm Europa's habitability, a new generation of missions will follow. More ambitious, more complex, more focused on the ultimate question: does life exist in Europa's ocean? Several concepts are already in development. NASA and the European Space Agency have studied them for years. Some are decades away from launch. Others might fly within the next 20 years. Each pushes the boundaries of what is technically possible. The Europa lander is one such concept. A spacecraft designed to touch down on Europa's surface, to drill into the ice, to analyze samples in detail, to search for biological signatures that orbital missions cannot detect. Landing on Europa presents unique challenges. The surface is extremely cold. The terrain is rough. Sharp ice ridges could damage a spacecraft. Radiation levels are intense, and communication with Earth requires careful planning due to Jupiter blocking signals periodically. The lander would need to be autonomous, capable of selecting a safe landing site, making decisions without waiting for commands from Earth. The round-trip light time to Jupiter exceeds 90 minutes. Real-time control is impossible. Once landed, the spacecraft would deploy instruments. A drill would bore into the ice, perhaps 30 feet deep, perhaps deeper. The goal is to reach ice that has not been heavily processed by radiation, ice that might retain organic molecules, ice that might contain material from the ocean below. The drill would bring samples to the surface. Instruments would analyze them immediately. A mass spectrometer would identify molecules. A microscope would search for cells or cell-like structures. Chemical tests would look for amino acids, lipids, and other biological signatures. The lander would operate for perhaps 20 days, maybe longer if systems survive the radiation. It would transmit data constantly, every measurement, every image, every result. Then, as systems fail, it would go silent. Its mission complete. But even more ambitious concepts exist. The Europa Ocean Explorer, a mission that would not just land on Europa, but penetrate its ice shell. Deploy a submersible into the ocean itself, explore the alien sea directly. This concept pushes technology to its limits. The spacecraft would land on Europa. Deploy a heated probe. The probe would melt through the ice, slowly, over weeks or months, descending through the frozen shell. As it descends, the probe would analyze the ice, measure its temperature, its composition, look for layers that might indicate different eras of surface activity, document everything about the ice shell. When the probe reaches liquid water, everything changes. It would deploy a small submersible, untethered, autonomous, equipped with cameras, lights, and chemical sensors. The submersible would be on its own, free to explore. This submersible would search for hydrothermal vents, for concentrations of organic matter, for anything that moves, for any sign of life. It would sample water at different depths, image the underside of the ice shell, document the alien ocean. Communication would be the greatest challenge. Radio waves do not penetrate ice well. The submersible might need to return periodically to the hole, transmit its data, then dive again. Or it might trail a fiber optic cable, maintaining connection to the surface. The mission would be relatively short. Perhaps days, perhaps weeks if everything works perfectly. But in that time, it could answer questions that have haunted us for decades. It could discover life in Europa's ocean, or confirm that life does not exist there. Of course, such a mission is extraordinarily expensive, extraordinarily complex, extraordinarily risky. The probability of success might be low, but the potential payoff is enormous. Discovering life beyond Earth would transform our understanding of biology, of the universe, of our place in it. Other concepts focus on the plumes. If water geysers truly erupt from Europa's surface, they offer easier access to ocean material. A spacecraft designed specifically to sample plumes could gather data without landing, without drilling, simply by flying through the erupting water. Such a mission would be simpler than a lander or submersible, but it depends on the plumes being active, being predictable, being large enough to sample effectively. Current observations suggest plumes are intermittent. They might erupt for hours or days and then stop for months. Timing would be critical. The European Space Agency is developing its own mission, JU-ICE. Jupiter, Icy Moons Explorer. Launched in April 2023, it will arrive at Jupiter in July 2031. While its primary target is Ganymede, it will also study Europa during several flybys. JUICE carries instruments similar to Europa Clipper: cameras, radar, spectrometers, magnetometers. It will complement Europa Clipper's observations, provide additional data, different perspectives. Together, the two missions will give us unprecedented knowledge of Europa. Beyond these planned missions, scientists envision even more ambitious concepts. Constellations of small satellites orbiting Europa, each carrying specialized instruments, working together to map the Moon comprehensively, to monitor changes over time, to watch for plumes and other dynamic events. Some concepts involve long-duration surface missions, nuclear-powered landers that could operate for years, studying how Europa changes with seasons, with orbital position, with the 11-year cycle of Jupiter's magnetic field activity. Others propose aerial vehicles, balloons or drones that could float in Europa's thin atmosphere. Survey large regions quickly, identify targets for future landers, though the atmosphere is extremely thin, making flight difficult. Each concept brings challenges. Each requires technologies that barely exist. Each demands enormous resources, but each also promises answers. Piece by piece, mission by mission, we will unravel Europa's mysteries. The timeline for these missions spans decades. Europa Clipper arrives in 2030. JUICE arrives in 2031. Both complete their investigations by the mid-2030s. Analysis of their data takes years. Planning for follow-up missions takes more years. A lander might launch in the early 2040s, an ocean explorer in the 2050s. This is the pace of space exploration: slow, deliberate, each mission building on the last. Each discovery informing the next step. But the direction is clear. We are going to Europa. We are going to search for life. We are going to answer the question that has fascinated humanity since we first learned an ocean exists beneath that frozen shell. Will we find life? No one knows. The ocean might be sterile. The chemistry might be insufficient. The energy might be too limited. Life might require something Europa lacks. Or we might discover organisms thriving in that dark ocean. Alien biology. Different from anything on Earth. Proof that life arises wherever conditions allow. Either answer would be profound. Europa is more than just a moon. It represents a fundamental question about our existence. Are we alone in the universe? Or is life common wherever conditions allow? The answer changes everything. For most of human history, we assumed Earth was unique, special, the only place where life existed. This made sense. We saw no life on the Moon, none on Mars, none anywhere we looked. Earth seemed to be an exception, a rare occurrence in a lifeless cosmos. But Europa challenges that assumption. Here is a world with no sunlight reaching its ocean, no photosynthesis, no oxygen atmosphere, yet it has all the other requirements for life: water, energy, chemistry, time. If life exists there, it means life does not require Earth-like conditions. It means biology is more flexible than we thought, and if life arose independently on Europa, the implications are staggering. Life would have originated at least twice in our solar system, on Earth and on Europa. Two separate genesis events, two different trees of life. This would suggest that life is not rare, that given the right conditions, biology emerges naturally. Our solar system contains 8 planets and over 200 moons. If 2 bodies host life, the probability that others do increases dramatically. Mars might have harbored life billions of years ago. Enceladus, Saturn's moon, also has a subsurface ocean. Titan has liquid methane lakes. Each could potentially support some form of biology. And if our solar system alone contains multiple instances of life, what about the galaxy? Billions of stars, trillions of planets, countless moons. If life is common rather than rare, the universe might be teeming with biology. We might live in a cosmos where life is the rule rather than the exception. This possibility reshapes our philosophical understanding. We would no longer be special, no longer alone. We would be one example among countless others. Life would be a fundamental characteristic of the universe, as common as stars and galaxies. But even if we find no life on Europa, the answer matters. If Europa is sterile despite having all the necessary conditions, it tells us something important. It suggests life requires more than just water and energy. Some additional factor, some spark we do not yet understand. Perhaps life requires specific chemicals we have not identified. Perhaps it needs particular temperature ranges. Perhaps the origin of life is so improbable that even billions of years in a habitable ocean is insufficient. This would suggest we are alone, or at least very rare. Both possibilities are profound. Both change how we see ourselves. Finding life makes us ordinary. Finding no life makes us precious. Europa also tests our technological capabilities. Can we build spacecraft that survive extreme radiation? Can we drill through miles of ice on another world? Can we deploy submarines in alien oceans? Each mission pushes engineering to new limits. Success demonstrates our growing mastery of space exploration. The search for life on Europa unites humanity in common purpose. Scientists from dozens of countries collaborate on mission planning. Engineers share technologies. Data is openly published. Everyone participates in the discovery process. In an often divided world, the search for extraterrestrial life reminds us of shared curiosity. Common goals. Young people today are growing up knowing that missions to Europa are real. Not science fiction, but actual spacecraft being built and launched. Students studying astrobiology might someday analyze samples from Europa's ocean. Engineers learning robotics might design the submarines that explore alien seas. The search for life beyond Earth inspires the next generation. Europa also raises ethical questions. If we discover life, how should we treat it? Do we have the right to sample it, study it, potentially harm it? On Earth, we struggle with conservation of our own planet's biodiversity. How much more carefully should we treat life that evolved independently? Planetary protection protocols already exist. Strict rules govern how spacecraft are sterilized, what regions can be explored, how samples must be handled. These rules will become more stringent if life is confirmed. We cannot risk contaminating Europa with Earth biology. We cannot risk destroying what might be the second genesis of life. Some argue we should not visit Europa at all, that we should leave it pristine, untouched, a preserve for alien life to continue evolving without human interference. Others counter that understanding Europa's life could teach us fundamental truths about biology, that the knowledge is worth the careful, controlled risk. These debates will intensify as missions progress, as capabilities improve, as the possibility of reaching Europa's ocean becomes real. Society must decide how to balance scientific discovery with preservation, how to explore while minimizing harm. Europa also connects to our search for life beyond the solar system. Thousands of exoplanets have been discovered. Some orbit in their star's habitable zone. Some might have oceans. If we understand how life could arise on Europa, we better understand where to search among the stars. Telescopes are being built to analyze exoplanet atmospheres, to search for biosignatures, gases that indicate life. But we need to know what signatures to look for. Europa provides a test case. If life exists there without oxygen or photosynthesis, we must search for different signatures on distant worlds. The search for life is ultimately about understanding our own origins. How did chemistry become biology on Earth? What conditions allowed life to emerge? Is there something special about our planet? Or did we simply win a cosmic lottery that plays out billions of times across the universe? Europa offers clues. If life arose there, we can compare it to Earth life. Identify what is universal versus what is contingent. Understand which aspects of biology are fundamental and which are accidents of history. Perhaps Europa's life uses the same genetic code as Earth. Perhaps it uses DNA and RNA. This would suggest these molecules are special, uniquely suited for storing information, universal solutions to biological problems. Or perhaps Europa's life uses completely different chemistry, different information storage, different metabolism. This would prove biology is more diverse than we imagined, that multiple solutions exist to the challenge of creating life. Either way, we learn something profound about life itself. Europa sits out there, orbiting Jupiter, keeping its secrets beneath miles of ice. For now, we can only wonder what swims in that dark ocean. What strange organisms might call it home? What alien biochemistry might thrive there? But we will not wonder forever. Missions are flying, instruments are being built, plans are being made. Within our lifetimes, we may know the answer, and that answer will change us. Our journey to Europa ends here, but the real journey is just beginning. Somewhere beyond Earth, beneath frozen ice, an ocean waits in darkness. We have never seen its waters, never touched its shores, never glimpsed what might swim in its depths. Yet we know it is there. Physics tells us. Magnetism proves it. The cracked surface reveals it. Europa represents hope. Hope that life is not confined to Earth alone. Hope that biology emerges wherever conditions allow. Hope that we live in a universe rich with living worlds, rather than cold and empty. The spacecraft we send are our ambassadors. They carry our curiosity across the void. They ask questions we have wondered about for generations. They seek answers that will echo through history. In a few years, Europa Clipper will arrive. Its instruments will scan the frozen surface, measure the ice thickness, search for plumes, map the terrain. Each measurement brings us closer to understanding. Each data point adds to the picture. Future missions will go further. Land on the surface, drill through the ice, perhaps even swim in that alien ocean. Each step more ambitious than the last, each bringing us nearer to the ultimate answer. We do not know what we will find. The ocean might be lifeless, empty of biology, a sterile soup of chemicals that never crossed the threshold into life. This would be disappointing, but it would still teach us something important about life's requirements. Or we might discover organisms, simple bacteria clinging to hydrothermal vents, complex ecosystems thriving in the darkness, biology utterly different from anything on Earth. This would be transformative, revolutionary, the greatest discovery in human history. Either way, the search continues, mission by mission, discovery by discovery, question by question. Europa orbits quietly in the darkness, patient, ancient, holding secrets that have waited for billions of years. Soon, we will begin to uncover them. Thank you for joining this exploration, for wondering about distant worlds, for imagining what might exist beyond our home planet. If you enjoyed this journey through the cosmos, please subscribe to Sleepy Science Nights. We will continue exploring the universe together, one peaceful discovery at a time. Sleep well, dream of distant oceans, and wonder what swims beneath the ice.